Now, in addition to the apparent change of direction of light beams, as seen in different rest frames, we would also see a change in frequency. Okay, and this is something that was implied by our second equation over here. So what we'd like to do now is understand this apparent change in frequency. So let's write down this formula. Nu is equal to nu prime into 1 plus beta cosine theta prime over the square root of 1 minus beta square. So this formula tells us that if we had a frame S prime in which we saw a light beam moving at an angle theta prime, and we had a frame S with respect to whom this frame S prime was moving at a speed v. So according to S, the frame S prime is moving at a speed with speed parameter beta or speed v. The first thing is S would of course see a different angle. Okay, it would see an angle theta, but instead of seeing an angle a frequency nu prime, the observer in S would measure a frequency nu. Now, this is not surprising to us. Even without relativistic physics, we know that when you have a source that is moving, the frequency of waves that you would see would appear to be different in a moving frame. So let's just recap the original result that we're familiar with in Galilean relativity. So in Galilean relativity, if you have a source of light and it's coming towards you, so this is the source S prime, which is moving, and you are at rest. Okay, you're at rest in your rest frame, and the source is moving towards you with a speed v. So now let's imagine that according to S prime, in their frame, what it looks like is that they are at rest and they are emitting light beams, and these the wavefronts of the light are emitted at every time interval t. So after time interval t, they will emit a set of waves, okay, or a wavefront, and this inverse of this time period is the frequency, okay, and these wavefronts travel outwards with a speed which we'll call vs prime, and therefore the spacing between these wavefronts would be some lambda prime, and lambda prime times let's call this nu prime t prime times nu prime would be vs prime. Okay, so you'd have many wavefronts which are emitted from the source S prime, and these wavefronts would be uniformly spaced between themselves. Okay, and now let's see what an observer S would measure. So the first thing is that each wavefront, as it's emitted, would appear to have a speed. In Galilean relativity, it would appear to have a speed if the wavefronts are moving this way in frame S prime. They would also appear to have an additional speed of S prime, so they would have a speed vs prime plus v. Okay, that would be the speed of these wavefronts as seen by observer S. The second thing is that if I look at the spacing between these wavefronts, so let's imagine that we have a wavefront which is emitted at t is equal to 0, and this wavefront in a time period t prime would travel a distance vs prime plus v times t prime. Okay, this would be the distance traveled by that wavefront in a time t prime. After the time t prime, this source S prime itself would have moved to the right by a distance of v times t prime. Okay, and at this point, uh, the source S prime would emit a second wavefront. Okay, and therefore the spacing between these wavefronts, as seen by observer S, would be Vs prime plus Vt prime minus Vt prime, which would be Vs prime T prime. Okay, where Vs prime is the speed of these waves which are propagating as seen by observer S prime. In other words, this spacing between the wavefronts as seen by observer S, this would correspond to, let's say, one peak of the wave function. This is another peak. And so the spacing between the peaks is exactly the wavelength as measured by observer S. So this would be the wavelength measured by observer S. And also, the speed at which these waves propagate according to observer S would be Vs prime plus V. The speed of wavefronts as measured by observer S. So therefore, the frequency as measured by observer S would be equal to the speed as measured by observer S divided by the wavelength as measured by observer S. And this would be Vs prime plus V divided by Vs prime T prime. Now we can write the speed Vs prime, that is the speed at which the wavefronts are propagating in freemium S prime, in terms of Vs. So we can rather rewrite this expression as Vs over Vs minus V times T prime. Okay, so the frequency as measured in frame S is equal to Vs over Vs minus V times the frequency as measured by S prime. Okay, so Vs is the speed of propagation as measured by the observer S, or in the frame S, and V is the relative speed of the source. Okay, and in the limit that the speed of the source is much smaller than the speed of propagation of the wave, we can write this as just using a binomial expansion, we can write this as 1 plus V, approximately 1 plus V over Vs times nu prime. So in this limit, the shift in frequency, or that is the change in frequency, would just be equal to V over Vs times nu prime. Okay. So what we would expect if Galilean relativity was correct is that you should see a shift in frequency, if observer, uh, since the observer S is not moving and the source S prime is moving relative to them, the speed of propagation of these waves is c. And so what you expect is some kind of relationship like this. Okay, this is what you expect in Galilean relativity. So you do expect a shift in frequency. Even in Galilean relativity, you don't expect the frequency measure to be the same, and this effect is called the Doppler shift. And you can see a couple of things. One is if the speed v is positive, that is, the source is moving towards the detector, or in the direction of emission, then nu is greater than nu prime. So the frequency is larger, or you would say that the wavelength is smaller. And if you think about the visible light spectrum, okay, so the visible light spectrum, let's say, goes from blue to red. Blue colors are high frequency colors. Okay, the wavelength of light is smaller, or they have larger frequencies, and red is low frequency. So if the frequency that you detect is larger than the frequency emitted, so let's suppose you're emitting a frequency here, the frequency that you detect is actually here, if you're in frame S, so that's new. So you would say that the light is blue shifted. And similarly, if V less than 0, then nu would be less than nu prime, and the shift would actually be in the other direction. Okay, and you'd say that the light is red shifted.